In our previous video, we have highlighted 8 coding guidelines for better synthesis. We will be discussing each in detail in the upcoming videos. Let us look at the differences between blocking and non-blocking assignments. Blocking assignments. The blocking assignment operator is an equal sign. A blocking assignment gets its name because a blocking assignment must evaluate the RHS arguments and complete the assignment without interruption from any other Verilog statement. The assignment is said to block other assignments until the current assignment has completed. The one exception is a blocking assignment with timing delays on the RHS of the blocking operator, which is considered to be a poor coding style. A problem with blocking assignments occurs when the RHS variable of one assignment in one procedural block is also the LHS variable of another assignment in another procedural block and both equations are scheduled to execute in the same simulation time step. When modeling combinational logic, use blocking assignments. The post-synthesis combinational design functions exactly the same in both blocking and non-blocking assignments, because a netlist generated is the same for both the codes. We will discuss this in details with an example. Only the functional simulation will have different outputs generated basis on the type of assignments used. If we don't follow the guideline of using blocking assignments for combinational logic, then we might have a results mismatch between functional simulation and post-synthesis. Let us consider an example and discuss further. The code shown in example 1.3 generates the Y output from 3 sequentially executed statements. Since non-blocking assignments evaluate the RHS expressions before updating the LHS variables, the values of TMP1 and TMP2 were the original values of these two variables upon entry to this always block and not the values that will be updated at the end of the simulation time step. The Y output will reflect the old values of TMP1 and TMP2, not the values calculated in the current pass of the always block. This code is logically correct, but results in mismatch between functional and post-synthesis simulation. The code shown in 1.4 is the right example of coding a combinational circuit. Usage of blocking assignments makes sure that output Y is updated with the latest values of inputs A, B, C, D, and avoids any mismatch between functional and post-synthesis simulation. As shown above, the post-synthesis schematic generated for both 1.3 and 1.4 example codes is the same. It means, post-synthesis, they function exactly the same, but will have different behavior in functional simulation.